Hello, everybody, and welcome to a new session of the HPP Innovation Week, the benchmark event on high-pressure processing for the food and beverage industry. This is Oscar Garcia, Sales and Marketing Specialist at Hyperbaric. And first of all, I would like to remind all the attendees that we have an open chat where we will be trying to answer all the questions that we received. During this session, we are going to discuss how HPP offers self-refrigerated beverages with an extended shelf life. For this, we have two great speakers with us. They are Dr. Jessie Usaga. Hello, Jessie.
Hi, Oscar.
And George Hughes Davis. Hello, George.
Yeah.
Okay, so now let me explain a little bit the structure of the session. So the session will be as follows. Jessie and George will give their respective individual presentations. And right after each presentation, I will ask a couple of questions to both of them. Okay, so
Good.
perfect. So let's start with you, Jessie. So I will introduce her a little bit. Dr. Jessie Usaga is a professor of food processing at microbiology, at the University of Costa Rica. She received a bachelor's degree in food science at the University of Costa Rica and a PhD in food science at Cornell University, where she later held the position as a visiting associate professor and coordinator of the HPP Validation Center. Dr. Isaga's primary focus of research includes fruit and vegetable processing and microbiology. Her expertise areas include food safety, non-thermal and thermal processing, and uses safety and spoilage control. Okay, Jessie, so the audience is eager to listen to you. You are sharing your screen perfectly. We can see it in full screen. So yes, go ahead.
Thank you very much, Oscar, for the kind introduction and, of course, for the invitation. It is an honor to collaborate as a speaker at the 2022 HPP Innovation Week. So today, I'll share with you the main results related to our research that is about the evaluation of high-pressure processing inactivation of three pathogens of concern: E. coli, Salmonella, and Listeria monocytogenes in acid and acidified beverages. It is important to mention that this research was performed at the HPP Validation Center at Cornell University with collaboration with researchers from Cornell University. These experiments were performed at a biosafety level 2 laboratory using a commercial scale unit that is available at the validation center for industrial purposes for the execution of microbial safety validations. It is important to mention as well that this study was published in 2021. So the information is available out there, so you can review the manuscript in case you have additional details that I would like to go over. So this investigation was motivated considering some of the industry challenges that they were facing at the time that the experiment was performed. So, for example, we were aware that there were some questions about what is the most resistant and the pertinent pathogen of concern in this kind of products. We also knew that there were not that many laboratories offering the service to perform microbial safety validations. And then in some cases, the cost was prohibited for small and medium scale processors. So we wanted to generate baseline information, scientifically baseline information that industry might be used. And we were hoping to develop enough information to eventually use these results as the baseline to establish a safe harbor. By safe harbor, I'm talking about the development of a procedure that is recognized and that can be employed by industry without further validation. So this was like the first step of developing a safe harbor for the application of high pressure processing in acid and acidified beverages. So for that, the experiment was divided in two parts. In the first part of the experiment, we used commercially available, shelf-stable, preservative-free, 100% apple juice. And the objective was to determine the pressure tolerance of the three pathogens of concern in acid and acidified products using a 5-strain cocktail for each of the pathogens. We used strains that were previously linked to outbreaks in the United States. So the 5 strains were pathogenic strains. And then we inoculated the samples, targeting an initial population of 7 logs of each of the pathogen. All experiments were independently performed. And then after that, we apply different high pressure processing conditions. We evaluated different pressures, including 400, 450, and 475 megapascals. And we use different exposure times from 9 minutes for E. coli and from 1 to 7 minutes for Salmonella listeria. These conditions were established based on preliminary trials. And then after applying the treatment, we calculated the log reduction of each of the pathogen using a standardized FDA bacteriological analytical methodologies, and determined the population of each of the pathogen before and after treatments. Samples were refrigerated at 5 degrees C, and then the conditions, the machine that we used was controlling the pressure, the processing time, and also the water temperature, and all conditions were recorded. So we have that information available in the paper. Going on with the results, we did something that we adjusted the pH of the apple juice because we wanted to use a higher pH, 4.5 pH. And the thing is that we adjusted the pH to 4.5, taking into account a critical limit that prevents Clostridium botulinum spores from producing toxin in foods. And the fact that graded inactivations, you can see graded inactivations by HPP when using pH below that value. So we wanted to work under the worst case scenario. Then on your right, you'll see in figure 1, we have the inactivation kinetics for E. coli is A, Salmonella is B, and Listeria monocytogenesis is C. And we have that at the different pressures that we evaluated. And then we analyze the data using 2 different models. We use like a first order model, the log linear model, but we also use the Weibull model. And in all cases, you can clearly see that the survival rate of the pathogens decrease with increasing the pressure treatment. Higher treatment pressure increases the inactivation rates regardless of the pathogen evaluated and the product evaluated. And then we also found that a Weibull model better described the results of inactivation kinetics than the log reduction model. Then we calculated the pressure tolerance parameters for each of the pathogen using both models, and we have the results right here in this table. As you can see, there are different values for each of the pathogen, different times required to achieve a 5 log reduction, which is the standard required according to the juice hazard regulation established by the FDA. So in all cases, we found that we need more time to inactivate E. coli than Salmonella and Listeria monocytogenes. So in that case, we concluded that E. coli is the most pressure-tolerant pathogen from the 3 that we evaluated in acid and acidified beverages. In this figure, you see also the predicted treatment pressure and times combination required to achieve a 5 log reduction. We compared that with the standard. We were aware that most companies were using a treatment of 600 megapascals for 3 minutes. That is a typically used processing combinations in the food industry. So we found that with our results, to produce a 5 log reductions of E. coli, Salmonella, and Listeria, we needed 3.2, 1.8, and 2.1 minutes to achieve a 5 log reduction. So we were very close to achieve a 5 log reductions with 3 minutes, but according to the predictions, we needed more time than 3 minutes, not just 3 minutes. But that's why we decided to perform a verification study. In the verification study, that was the second part of the experiment, we used fruit and vegetable juices that were already available in the market. In this table, you can see the description of the 11 juices that we use for the verification experiment. And here you can see all the ingredients that were reported in each of the label. Then you can see also the physical chemical profiles of the different products. You have the pH, the water activity, the total soluble solids, and also turbidity. What we wanted to see is if our models was properly predicting the inactivation rates that we would expect when applying the treatment. So for this experiment, we decided to work only with E. coli because we found that it was the most resistant pathogens from the 3 pathogens evaluated. So samples were inoculated with pathogenic strains of E. coli. We kept the samples at 5 degrees C. Then we apply a high pressure processing treatment at 550 megapascals for 1 minute. And then we calculated the log reduction of E. coli, considering the population before and after treatment. And then we found that in all cases, the log reduction obtained experimentally was always higher than the predicted value. That means that our model is conservative and that it might be safely used to calculate the inactivation rate of E. coli in acid and acidified beverages. Worth mentioning, we also evaluated the effect of refrigerated storage on the survival of the pathogens after treatment. So in figure 3, here on your right, you'll see for the 3 pathogens, for E. coli, Salmonella, and Listeria, that we evaluated the survival, the log reduction obtained after 24 hours, 48 hours, and 72 hours after HPP, keeping the samples under refrigerated conditions. In some cases, we didn't see differences based on the storage time, but for the case of E. coli specifically, we saw a significant reduction of the population after 3 days of refrigerated storage after HPP. So that is an important element to take into consideration when you are designing a new process conditions for a new product development. Then in table 4, what you can see here is the experimentally observed log reductions of E. coli in the 11 juices that we evaluated using 550 megapascals for 1 minute. And then you can see the results, the inactivations obtained right after the treatment, 24 hours after the treatment, and 48 and 72 hours after the treatment. In all cases, you'll see that we achieve a greater than 5 log reductions, which means that these conditions are adequate to ensure the safety of these 11 fruit juices. So based on that information, our main result is that for all tested commercial scale juices or beverages, an HPP process conditions of 550 megapascals for 1 minute, which is less severe than the conditions currently used by the juice industry, that may help you to achieve a greater than 5 log reductions of Salmonella, E. coli O157H7, and Listeria monocytogenes. Then we know that these conditions or more severe conditions will ensure that HPP is an effective control measure that can be included in the juice hazard plan. So based on our results, we were very proud to conclude that the HPP conditions that are currently used by the juice industry, which are 600 megapascals for 3 minutes, those are the typically used conditions in the food industry. Those are good enough to meet the performance standard of the juice hazard rule for control of these 3 vegetative pathogens of concern. But using only acid and acidified juices and beverages with a pH below 4.5 and with physical chemical characteristics similar to the ones that we reported in our research. So we hope that our results from this study can be used by food processors and also by process authorities and regulatory agencies to support validation studies. We really hope that this information might be useful for the future establishment of safe harbors for the HPP industry. And with that, we may decrease the cost associated with the execution of safety microbial validations for each product that is going to be launched to the market. So with that, let me see if you have any questions. I'd be happy to answer as many questions as you may have. Thank you very much one more time for the invitation. It is an honor to be here.
Thank you so much, Jesse, for your presentation and really to explain in a really clear way the all your experiments and research. And I think it really have strong conclusions showing the effectiveness and of the effectiveness of HPP to inactivate pathogens. And okay, now I will formulate a couple of questions to you, Jesse. First
Sure.
one, what additional research would be needed to achieve a safe harbor for high pressure processed acid uses?
That's a great question. So going back to the definition of a safe harbor, that is going to be at the end the critical limits that you're going to apply and that are going to be established and recognized for food safety validity. We hope that in most cases that information will be available and published in federal performance or also guidelines, or regulatory authorities will publish that information. So we must be sure that these conditions will work under all case scenarios, even under the worst case scenario. So it's not like a simple task that we would perform only one experiment and then you'll have a safe harbor. It's not like that. So taking that into consideration, I think that we need to collect data from safety validation that have been already performed. There is much information available already in the industry. So we may statistically analyze that information, considering also the physical chemical profiles of the product to see if this trend is kept, to see if what we found in our study is what the industry is observing using different formulations. And we also think that it's important to understand if bacteria may adapt to certain conditions, for example, acid adaptation, of water activity adaptation, and if that may change the survival rate of the pathogens. And there is an important fact is that we didn't evaluate all the pathogens that might be present in these products. So for example, in apple juice, we have reports of outbreaks with parasites. For example, Cryptosporidium parvum. We didn't evaluate that. So it would be great to collect that information to see if this treatment is going to be good enough to also eliminate those pathogens that we know that are of concern in certain fruit juices. So I think if we can collect that information, we can safely say that we finally have a safe harbors, and we hope that it will be available soon, right? Because industry is needing that information to deliver the product safely to the market.
Yeah, that would be great. Thank you, Jesse. Very clear. And let's see if some of your colleagues, your research colleagues, is listening to this session, and maybe why not they start these kind of studies.
Open to collaborations, of course. Yes.
Okay, perfect. Okay, let's go now for the second one. So, in addition to physicochemical characteristics, sorry, of acid uses, do you think that ingredients play a role in microbial inactivation by HPP?
Okay. So ingredients will always influence the inactivation of different pathogens using different technologies. So I think that they may be naturally occurring antimicrobial compounds in some products. It will be great to understand what is the impact of those antimicrobial compounds in the final reduction, right? That is something that must be studied. It's not like that you can predict with no application to experiments. I also think that the composition of a new food product will change the physical chemical profile of a product. So it's going to change the pH, the water activity, the soluble solids content. So the formulation indeed will impact the effectiveness of the technology. But as you saw in our results, we have 11 different juices with different characteristics and different compositions. And we were able to achieve a failure reductions. In some cases, higher than 5, but always higher than 5, right? And in all cases, the treatment was safe enough to ensure the safety of the product. But I will definitely say that ingredients may impact the inactivation rate of different pathogens, but I cannot say for sure what would be the ingredients that you need to add or what will be the effect without having data to support that information.
Okay, fair enough. Okay, thank you, Jesse. So that's been all from our side for the, let's say, the academic and more technical and experimental perspective. Now it's time for George. So yes, so George founded Daily Dose from his mother kitchen back in 2016. Daily Dose has since grown to become the largest dedicated cold press juice manufacturer in the UK. And the company works with British farmers to source local produce and utilizes HPP to bring fresh, nutritious products to consumers across the UK and further afield. So, George, the floor
Hi,
is yours.
cheers. Thank you
Are
for
you
having me here at the talk. Yes, I'm going to give you a little bit of an overview about Daily Dose and a case study of the application of HPP sort of in industry. So, as you mentioned, Daily Dose is the only business in our category within the UK that's grown organically end-to-end production to distribution from when we started with HPP in-house. So we work to understand the product, the consumer, and then also the cold pressed juice market within the UK. So, as you mentioned, I started Daily Dose out of my mother's kitchen 6 years ago with the initial goal to fight food waste. Now we operate the largest cold pressed juice factory in the UK. We've got a 40,000 square foot facility in Cambridgeshire, which is about an hour and a half north of London. And we work with local growers to source wonky fruit and veg. So fruit and veg that's misshapen, too large, too small, bruised, which might otherwise go to waste. Then at the other end of the process, we take the leftover pulp and that gets turned into biofuel using an anabolic digester. So there's no waste throughout the whole process. In terms of our USPs at Daily Dose, the main one is that we produce in-house and in HPP in-house. So most juice companies in Europe and especially in the UK don't manufacture, they outsource their production to third parties. So for us, working with suppliers and sourcing produce was really, really important to help us fight the food waste epidemic. As I mentioned, the organic waste is turned into biofuel. And one of our major USPs is quality and taste. And HPP is part of that in terms of providing quality and maintaining the taste. So now we have the benefits of HPPing in-house. So there's a number of different benefits. The first that we see is the quality. So using HPP other than instead of methods such as pasteurization allow us to maintain the same quality on day one as we get on day 40. So we see we've done taste tests throughout the whole shelf life of all the juices and find that there's very little to no change in the quality of the products. The second is the improved agility and MPD. So prior to having an HPP in-house, we were working with a third-party toller. Having the machine in-house allows us to innovate, create new recipes, new products, and stay on top of market trends. So looking at what people are doing in different countries, traditionally America and Australia are a few years ahead, and now parts of Europe, the UK market. So we're able to look to see what they're doing in terms of innovation, new product lines, and then do those all in-house, and then do trials in-house using the HPP machine. One of the major benefits of having HPP in-house is the improved margin. So as I mentioned previously, we were using a toller. Having an HPP machine in-house allows us to save on the miles transporting product from our site to a third-party site, and also not paying a third party to toll each product, and normally it's done on a unit basis. Also, as you grow, you then benefit from the economies of scale of having it in-house. So you've got the same cost and overhead, but you're putting more product through the machine. In addition to that, we can also get more additional revenue through using spare capacity for private label. So as we've grown, we produce products for other companies using their own brands or own labels, which helps us to fill the capacity of the machine. Obviously, the main reason for using HPP is the improved shelf life. So when we first started back in my mother's kitchen, we were getting sort of 3 to 4 days shelf life. And now with HPP, we're seeing 60 days plus on many of the products, which makes a massive difference in terms of creating a commercially viable product. And then we've also got the improved sustainability, improved efficiency. So having everything under one house, not having to transport to third parties. And as mentioned, the sustainability of reducing the transport. Here's just a little graph showing some of the differences you see in terms of HPP pressure. So these are all results that we have across 3 different lines. So health shots, so ginger and turmeric shots, amongst some others, pure orange juice, and then mixed juices, so juices with more than one ingredient, so vegetable and fruit mixes, vegetable-based juices, or purely fruit-based juices. So you'll see on the left, when we started with health shots, we were getting sort of 3 to 4 days. Now we're getting over 60 days across all shot lines. Interestingly, going back to what Jessie was saying, we're currently processing 3 minutes at 6,000 bars or 180 seconds. And we're running trials to see what we can do to bring that down, to reduce the hold time and also the pressure. So looking at doing tests at 2 minutes, 1 minute, and also doing it at 5,500 bars, 5,000 bars, to increase the output of the machine we have. Then orange juice, similarly, we're getting 60 days. And when we first started testing mixed juices, we were getting 40 days. And now we're getting results back at 55 days. And just a quick look at the supply chain and showing what that does in terms of to the end customer. So originally we were getting 3 to 4 days, which really wasn't sustainable and wasn't viable to grow the business. So then we moved over to HPP, which, looking at sort of the average product, which is about 40 days, you look at production day 1 and then gets transported with 39 days shelf life left on it. Then gets the distributor and typically will be there for about a week or so before it ends up with the end consumer, and then delivered to the end consumer with a month's shelf life. So comparing that to before using HPP, you're sort of 10 times where we were in terms of shelf life at the end consumer.
Okay, great, yours. So great story here. So amazing. I mean, from since the beginning, when you started in your mother's kitchen, then started working with a toller, and you clearly explained the main benefits. Starting with a toller, I think is very valid and good option when you want to enter the HPP industry.
Yeah, it's a great way to sort of get your foot in the door and to start using HPP, seeing how it works, and helping you to scale to the stage where you can actually get your own HPP machine. So it's a great in-between step for growing the company.
Yeah, that's it. And then when you see that this is your technology, let's say you decide to implement it, and you explain very clearly the many benefits, that you can gain by having your own HPP machine. Regarding these kind of benefits, so I would like to drop you the first question. How has HPP helped Daily Dose open new market opportunities?
Yeah, so many ways. So there are lots of customers we couldn't reach before we had HPP in the shelf life. One that springs to mind is a supermarket in the UK. So we do all of their private label products, and prior to working with them, they had small juice bars in every single location, and they were having problems with consistency, quality, and also the shelf life. So they had a huge amount of wastage. They'd have a 2 to 3 day shelf life, making them on site. So trying to predict what the demand was going to be was nearly impossible without getting wastage. So they approached us. We redeveloped their recipes for them to work with the shelf life they needed in store, to try and achieve between 20 days on the higher pH products and up to 60 days on some of the lower pH products. And now we supplied their whole product range from smoothies, shots, juices, and flavored waters across all of their stores. So before we had HPP, that just wouldn't be an option for us. So it's brought them on as a new client, and also meant that we've brought their wastage down to nearly zero, improved the quality and consistency across all their sites. And then additionally, of course, export. So getting up to 60-day shelf lives opened up new markets for us in France and Belgium, and also in the UAE. So it's allowed us to branch out from the UK and reach out to customers who previously we just wouldn't have been able to reach.
Okay. Yeah, great to have here your own experience regarding this, the market opportunities that open thanks to HPP and the shelf life extension we can reach, but also in terms of sustainability, how we can fight food waste as well.
Yeah,
let's go with the second one here. What are your future plans to keep leveraging HPP?
Yeah, so new product developments. So we're looking at and doing tests on products with probiotics, prebiotics, added vitamins, and also smoothies, which are a relatively new product line for us. So functional smoothies, and seeing what the effects of the shelf life are on those, and seeing if we can achieve similar shelf life to what we get on the juices. Interestingly, from what Jessie was saying, one of the main things is trying to get more capacity out of the machine we have. So looking at the hold times and the pressure. So looking at the sort of trade-off between having 60 days and maybe 30 days, but being able to process 30% more. So if we're processing for 1 minute at 6,000 bars opposed to 3 minutes at 6,000 bars, we can get roughly 30% more product through the machine. So the main thing will be increasing the efficiency of the current machinery we have before we make the step up to buying a larger HPP machine and expanding our capacity.
Okay, great to hear about these expansion plans for daily dose. And come with our applications teams always when you start with this new product development phase and start with new things, you have always our applications team available to consult any technical issues or validation things. Okay, so
yeah, very much appreciate it.
For that.
We'll reach
Okay,
out.
Perfect. Okay, guys, so thank you both of you for your time here to this session. Thank you everybody on the other side of the screen, and just to encourage yourself to keep watching different sessions of the HPP Innovation Week. So yeah, once again, thank you everybody and goodbye.
Thank
Cheers.
you.
Thank you, Oscar.